Good morning, everyone. Fernand is my name. I'm from Dixieland in Germany. We are a company. We do power system software, simulation software, and we have been, over the last probably 10 years, quite active in terms of modeling of renewable energy. So my presentation today is dynamic modeling of variable renewable generation for grid integration studies. So we are going to focus on the dynamic aspects. And the idea could be not to jump too much into the details of a dynamic model. This could take quite long, but just to give you an overview, at least from the software developer viewpoint of the different models that we have available and what are the advantages and what are the disadvantages there, right? So I will start with a brief introduction just to put the topic into the context. Then an overview of these dynamic models, what has been the approach or what is the approach and the reason for the different models that they are around. I will touch also what are the pros and cons, also what are the advantages and disadvantages, and also an important thing which will be all interested, I guess, is the portability. That means how we can use the models in different simulation platforms. Yeah? At the end, we are in a multidisciplinary team with different tools around, and then we want to use one model developing one tool in the other one, and so on. So this is also a key issue. Then when different models with different complexity around, then we should have some criteria how to select which one is the best model or the appropriate model for the specific application. And then finally, I will touch a little bit the model validation. Yeah, a model is a representation of a real piece of equipment there. It will not be one-to-one. That's why it's a model. And the question is how close do we get the model for that specific application? And then I will summarize the presentation and give you an outlook at what, from our perspective, should be the next steps. Yeah. So as an introduction, one question is, what makes renewable generation a unique, or what are the unique characteristics? And these characteristics are challenging also the development of a dynamic model. So dynamic models have been around for a while, yeah, for conventional generation. And there was always a discussion, when you look at the dynamic model of a big nuclear power plant, there have probably not been so many discussions around us for the discussion of the dynamic model of a 5 megawatt wind turbine. I think there are different reasons why it has been like this. So the first one is what makes the model, the complexity of the model. The first one might be the large number of small individual units that we have, and this covering a large geographical area. So it's not like we have one big generator, but we have a power plant with many, many generators. Just to give you some figures, in Germany, roughly about 23,000 wind turbines, yeah, totalizing about 53 gigawatts of power capacity, and around 1.4 million of PV systems. Yeah. So if we want to put all this in a simulation model, yeah, it could be challenging also in terms of the simulation performance and data handling, etc. So this is an aspect we want to take into account, or we have to take into account. And the other aspect is also the dynamic performance, other than, for example, for a conventional power plant, is in case of renewable largely depending on the converter controllers. Yeah? So they are most of them converter-based generation, and that makes then converters are quite flexible in terms of performing multiple control functions. And at the end, how the generator will behave will depend on the controllers, yeah, which in many cases are manufacturer specific. Yeah? And the other important things to consider with regard to the conventional one is that the dynamic response is usually much faster than that from the conventional generation. And the other thing, we should maybe keep an eye on that, and I think this could be also good handover for the next presentation as well, is that the fact that renewable generation are partially embedded in distribution systems. So if we want to model them, we need to account somehow for the distribution system or for this embedded generation, right? We are observing now in Germany the discussion that the dynamic performance of the embedded generation is getting more relevant for the stability of the system, also in terms of providing ancillary services, as we have seen in some other presentation. So just to give you an idea, in Germany, around 95 to 98% of the PV generation, yeah, the total is about 41 gigawatt, are connected to the distribution network, right? So in terms of dynamic modeling, we need to account for them somehow. And it would be almost impossible, to account or to add standard models of PV and wind turbines to the system without getting some kind of aggregation before. So in terms of the requirements to the model, I will maybe highlight here 4 main points. The first one is the accuracy. Yeah, the dynamic response of the model, yeah, the idea is that it should replicate with sufficiently accurate the real behavior of the equipment. And sometimes the most sophisticated model does not always is the best one for a particular study. I mentioned that sometimes we tend to oversize the model, and we take in the belief that if the model is complex, the result would be better. It's not always the case. Yeah? So the model has to be really fit for purpose. Yeah? Another important issue is the numerical stability. And numerical stability of the model means that the model can work with integration steps, the simulation time step, typically used for stability analysis in network. We're talking about here half a cycle, so 50 Hertz system would be 10 milliseconds. You will see that some of the models you really need to go down just because of the numerical stability, sometimes 1 millisecond, etc. If you want to do a study at large scale, this would really be challenging. Yeah, I mentioned already portability of the model, so that you can use the model across different platforms. And at last but not least is the simulation performance as a requirement. Yeah, in particular, when we look at bulk power system studies, just to give you an example, to put some figures here around, if you look at the ENSO-E network, also the interconnected simulated like 10 seconds in, really 10 seconds in computation time. If you now include renewables, this will look different, yeah? So we'll have certainly a factor in between. And of course, if you want to go one step further and include distributed generation, will even go, the performance will go down. So when looking at bulk power system stability analysis, we need to have models which do also perform well. So these are more or less the requirements. Let's have a look to the classification of the dynamic models. And I will group here that there might be some other ideas around, but in 3 main groups, which are following more or less the historical development. Yeah? So the development of the technology. At the beginning, when a new technology is coming in, we put a lot of emphasis on getting all the details, yeah, because we are not really known, or the experience is a lack of experience, what would be the implication. And that's why you start with very detailed models, and then once you are getting more familiar with it, you start to simplify until you end with some generic models, right? So we start with the first one, which is the what we call a detailed EMT type model. So EMT means electromagnetic transient simulation. This is the most detailed or accurate model that we can have in terms of simulation, right? What are the characteristics here? First of all, is a three-phase model, instantaneous value. So you model really all three phases, A, B, C, and all the couplings. And important here is that you get also a detailed representation of the internal components. So typically, power electronics, you'll have IGBTs, right? You may have also some diodes or thyristors for protection, etc. This would be included in the model. In terms of the control, of course, you need to include the firing of the single components of the single IGBTs, yeah. And because of the frequency, you have the modulation frequency, you will need to have a time step size certainly below 1 millisecond. So we are talking about probably here some microseconds, yeah. Of course, advantage is you get a really accurate representation, and this is what you can do. You can later use the model as a benchmark. Also, you can benchmark other models against the EMT model. And they can also be used for internal faults. That means if you want to look into the model, some interaction between electromechanical parts, the control, etc., is something the model is actually adequate for that. Of course, a little bit the cons, yeah, and within quotes, yeah, because it depending what you want to do, if really a con or not. They are all of them manufacturer specific, yeah, because you do not get normally the details of how you control the different components, etc. Also, the control logic. So at the end, you have a black box model, yeah? And that makes also that the portability of the model is rather limited. Yeah? So you will get a model developed for a particular tool. You will be able to use it there, but not to use it in another simulation tool. So in terms of the graphic, also let's say of the component, just to put a simple an example of this could be a double FET induction generator. This is how the model on the top, you see how the model looks like. And here left at the bottom you see the representation. While you can see that for the PWM converters, actually you are using the a representation of the converter bridge, yeah, with the IGBTs. Yeah. On the right-hand side of the slide, you see the result of the simulation, instantaneous values, and then you can see also the effect of the different modulation, control logics, etc. Also in terms of the harmonics, you can get in the EMT world, you can get a good representation of that. So this could be the first one. So if we recall the previous slide, we can go from the EMT detailed model to the next one, which could be the detailed RMS type model. And these are probably one of the most commonly used. So what is the main characteristic here? We're not talking about any more instantaneous values, but we're talking about fundamental frequency model. So we capture the effect, the behavior of the model at power frequency. And we neglect everything what is different than power frequency. So we cannot replicate a different time constant or harmonics, yeah, and so on. In general, you will have a positive sequence representation. This is what also most of the solvers will do. There is, however, the option to have a negative sequence model. Of course, this would require a negative, an unbalanced RMS simulation. Yeah? In Europe, for example, in Germany, they have started asking about negative sequence voltage control. In that case, you can extend the model to do that. The representation of the internal components, also do you still have internal components in the model, but we do not go to the switching level, but we use just an equivalent voltage or current source, yeah? Fundamental frequency. The model still can be used for internal faults, yeah? Is however not the main purpose. Yeah? The simulation step size, yeah, in best case could be around 1 millisecond. Sometimes you can go to 10, but it's not really always the case. Yeah? Against the pros, advantages are an accurate representation. We are talking about here, in most of the cases, of manufacturer-specific models, which are not open source. Yeah? And this is the models that you will typically use for example, if you want to certify a model, yeah, a wind turbine generation, you will undergo a certification process, and this is the type of model you will use there. Yeah. Again, cons, manufacturer specific, so black box representation, I should say not for all of them. Yeah, there are different wind turbine manufacturers, the models are open, so you get a quite a highly detailed model even as an open model. Yeah, and again, the limited portability. Graphically, the model will look like this. And you will see that in that case, you do not use the switch, the IGBTs, but we use instead a PWM converter. It's an equivalent voltage source. You will put on top of them a so-called fast control loop. Yeah, it's a current controller, a fast current controller. This will make the model behave as a current source. And on top of that, you have the external controller, which is giving you the characteristic of the turbine. Maybe one thing I would like to emphasize as a message here is there are solutions also for black box model. So it's not that you need to always to have an open model. And I would like to point out here your attention to the IC standard. Yeah, this is a way to overcome the portability across different platforms. The IC standard define, as a, doesn't matter where you develop the model, you can compile according to some rules given in this standard, so that you can take in another solver the model, and by the time you initialize the model, you can get the parameters, you can parameterize the model, or let's say get access to the different equations for the initialization, and also you can run the simulation, right? So basically you solve the differential equations there. So this is a good solution also. It's picking up, and we get more and more models which are developed. For example, this is just in a case has been developed in MATLAB. It's quite used at manufacturers, different manufacturers. They may develop the model in MATLAB. Then you can compile. There is a symbol encoder, so that you get basically the C code. Yeah. And then you can compile the model. In our case, our software Power Factory, you can then integrate the DLL into Power Factory. The solution, however, does also work for other tools. Yeah? And then we come to maybe the third and last category. Sorry, I skipped that. The so-called generic RMS type models. And here, again, characteristic, we are talking about a fundamental frequency model, as an RMS type, positive sequence representation. So far in the standards, you will only find positive sequence. And this is indeed an open source model. That means the standard, I put here 2, the IC or the WECC models in US, they document and they say, well, this is how the different blocks should look like. Yeah. Of course, you get some less detailed representation. This is true, but on the other side, doesn't mean that the model is not fit for purpose. Yeah. So depending on what you want to do, definitely it's not adequate for internal faults. But in most of the application, we look at the impact of the model on the network. And the other thing is, at least the standards they claim, the model can run for step size up to 10 milliseconds. Yeah. Pros, then the portability across the different simulation platforms, the transparency. There have been many presentations about open source. I mean, that you know what is going on in the model. What could be a con is that the manufacturer-specific characteristic, the idea is that they should give you a set of parameters to represent the behavior of their turbine using the standard model. Yeah? It hasn't worked really very good so far in terms of getting the parameters from the manufacturer, but I think there is some work still to be done. So the generic model follows a modular approach. Yeah, just here a simple representation. I took it from the IC, but you have something similar for the WECC, where you define the different blocks. You see the control basically interfacing with different blocks. You have the aerodynamic part, you have the mechanical part, the generator itself, then the measurement equipment, electrical equipment, and also the grid protection. Yeah, and the standard will give you for all the different blocks how the transfer function should look like with different parameters, and then, well, you know exactly what the model is doing. For that kind of representation, we can aggregate the model, so we don't need to go for all the internal representation of the internal components. Basically, what you do, you include the equations in your dynamic control, and then you only need, in terms of network interfaces, one component, which is at the end either a current source or a voltage source as an interface to the network. Yeah? In our case, we have a so-called static generator, we call it, that to represent whatever generation is connected through a converter. And it follows a functional specification, a functional approach. So basically, you have the different blocks with the different, let's say, characteristic of the model. I put here some of them. There are certainly not all of them, but for example, you see here 4x3 capability. The other one is a so-called dynamic voltage support. Yeah, so that's during the fault, you inject reactive power typically. Yeah. And for all of this, the standard will give you the control function and the parameters. Yeah? For example, typical here would be the K, so-called K factor. That is the gain between how much current you inject depending on the voltage step. You see on the right-hand side typical simulations. The other one could be, for example, the active power frequency response has been also discussed here with this 50.2 Hertz effect. That you have a ramp, you ramp down the output, or for example, you may have a ramp limitation also. The approach, as a small hint here in terms of analysis, the approach of these generic models goes actually quite good in line with the approach of the ENSO-E grid code. That the ENSO-E defines for power generating units different types from B, C, and D, depending on when connected to 110 kV or above 110 kV and different units. Yeah? So in terms of network planning, you know, if you're looking in 20 years now or 15 years, you even do not know which technology you're going to use, yeah? Depending on the manufacturer, etc. So the generic models are actually a good approach in terms of doing the analysis. You can follow and say, well, depending on the grid code, which functions, yeah, which ancillary service, etc., you can expect from the plant, okay, and parameterize the model based on that. And also the interfacing or the exchange of data on terms of generic models. There is a lot of work going on there. I would like to highlight the common information model. Here, this is an initiative from, among others, also ENSO-E, looking at the exchange of data initially for steady state, but we are now working also on the support of to support the exchange of dynamic data. So what they do is, well, all the software providers or software vendors there, based on the standards, on the generic models, yeah, which are being validated, etc. We developed the interface. It's an XML file-based interface so that you can exchange also across platforms the different parameters of the model. So the selection of the model, at the end we set considering model accuracy as a model adequacy and simulation performance and numerical stability. I try to put it here on the graphically. Not always the more complex one is the best one, yeah. And it's a trade-off, you know, when between the accuracy, the complexity of the model, and then simulation performance. So where to fit, where to find, it's the trick. Just to give you some idea. Okay, thank you. Just to give you some idea here, they put the table some application cases, and then you see on the 3 columns from the detailed EMT representation down to the RMS type and the generic. So you'll see that when you look at more the design things, yeah, like design of control system, the protection of the power electronic components, also torsional stress, yeah, if you have subsynchronous torsional interaction, etc. In that case, you will certainly need to go for the EMT detail models. Yeah? However, in that case, you may look at just a rather small part of the network. The next would be more the so-called grid code compliance study. So if you want to bring a new farm, a new park to the network, yeah, you need to demonstrate grid code compliance. And grid code compliance is also much dependent on the specific characteristic of the turbine. You will probably need to use a detailed manufacturer-specific model. Again, in that case, the performance might not be the big issue, yeah, but you may put the emphasis on the accuracy of the model. And finally, you have the classical transient stability or dynamic voltage stability, frequency stability, where you need to look at the system as a whole, yeah. Of course, you can still use detailed model if you do not care about the performance, but in a real application case, you will probably need to get some kind of simplification. You need to exchange data from other networks, yeah, and then the generic RMS type models are actually quite good, have demonstrated to be quite adequate to the simulation. In summary, you will see that mainly the first part is with the manufacturer, with the power park developers, while the lower part of the table is more for integration studies. And this is where you will move around. So finally, the model validation is also a good point. Yeah, when we present, sometimes the models say, well, but have you validated them or not? Maybe a good experience here has been done in Germany. So in Germany, I do not know if you are aware, but normally if you want to connect a power plant to the grid, you need to undergo a certification process. And to certify the process, you need to have a certified model. Yeah? So the FGW is an association in Germany, has developed a series of guidelines for the certification. There is a list in internet of certified models, so if you want to check, you can go there. Yeah? And I put here just a simple example of this of a validation model. This is one who has passed the certification. You see in red is the measure curve. Okay, just come to the conclusion. Yeah? And the blue one is the simulated one. You see that there are always differences, yeah, depending. For example, here is if you look at the EMT model, you will have a better replication, yeah, because you can consider saturation effects that you do not have in the RMS model. But depending on the constraints put on the model, on the requirements, you know, the model can be acceptable or not. Yeah? So just to conclude, we say the different models, yeah, from manufacturer specific to generic standard, they are both okay. Yeah, the manufacturer specific are typically Blackbox, the other one are open source model. Important is in terms of the simulation, they have to be fit for purpose. Yeah, so we need to think about what we want to do with the model. Yeah? Simulation performance is also an important issue, and then the portability of the model, and then you can work on these two things. Yeah, either to promote the use of generic models, yeah, as we do for conventional power plants, or if you go for manufacturer specific, you have the IEC standard. Yeah? And finally, an outlook. Certainly more further standardization is required in terms of dynamic for other systems like storage, yeah, battery storage system. Dynamic modeling of distribution network with embedded generation is certainly also an issue. Other FACS components are probably still missing, at least in the ENSO-E, in the European experience. Data exchange, yeah, the SIM for dynamic is ongoing. I think this will be also the future. And then maybe a last point I'm going to bring here to discussion is also the dynamic network reduction. So at some point you need to aggregate, you need to reduce, and how to do the network reduction, I mean a dynamic network reduction under consideration of the nonlinear behavior of the generation. Yeah? So that's all from me. Thank you for your attention. Yeah?